Good morning, students. In the previous classes, we have covered simplex method where we handled less than equal to type of constraints as well as mixed type of constraints. So in that context, we had studied big M method also. In this class, we will study some exceptional cases in the simplex method. So the first one is infeasible solution. So when we say that the solution is infeasible, okay, so when in the final simplex table at least one artificial variable is present in the basis with a positive value, the given linear programming problem does not possess an optimum basic feasible solution. So in this case, the problem has an infeasible solution. Second case may also arise in case of bigger method when at least one artificial variable is present in the basis with zero value. The optimum basic feasible solution is degenerate. Okay. So example we can take minimize of z x1 plus 2x2 plus x3 subject to the constraints x1 plus x2 by 2 plus x3 by 2 less than equal to 1. And the second constraint 3 by 2 x1 plus 2x2 plus x3 greater than equal to 8, x1, x2, x3 all greater than equal to 0. So if we solve this problem using simplex method and go to the last or final table, we can find there that basic variables are x2 and a1. x2 is having value 2 and a1 is having value 4. So I have encircled here this. We can observe that the artificial variable a1 is present in the final table, optimal table with a positive value 4. It simply indicates that this problem has no feasible solution. Okay, we can see from here all zj minus zj greater than equal to 0, but an artificial variable has a positive value, that is a1 is equal to 4 in the final table. Therefore, it has infeasible solution. Okay, so whenever you find this kind of situation in the final table, you conclude that this problem has infeasible solution, no feasible solution. The next case is multiple optimal solutions. In the optimal simplex table, if a non-basic variable has 0 coefficient in the zj minus cj row, means simply if any non-basic variable has 0 value in the zj minus cj row, then there exists an alternate optimal solution. This is because the non-basic variable can enter the basis without changing the value of the objective function z, but can cause a change in the values of the basic variables. This variable may be a decision or slack or surplus variable. Okay, what you have to do, you have to see in the basic variables column only. Okay, the other variables other than those appearing in the basic variables are treated as non-basic. So those non-basic could be your x1, x2, x3 decision variables. Those could be your slack or surplus variables. Okay. For example, maximize z is equal to 4x1 plus 10x2, and these are the constraints less than equal to constraints. So this problem possesses multiple optimal solutions. So if we go to its final table, optimal table, we can see here, this is the situation. Okay, all the Zj minus Cj greater than equal to 0. But you see, these are the basic variables x1, x2, s3, and other than these, that is s1 and s2. These are the non-basic variables, and out of these non-basic variables, this s1 is having 0 value in the Zj minus Cj row. So non-basic variable is has 0 value in Zj minus Cj row. This indicates that there will be multiple optimal solutions to this LPP or alternative optima. Okay, there could be another set of the basic variables like this, and the objective function value will be same for that. So in fact, it has a number of infinite number of multiple optimal solutions. Unbounded solution. An unbounded solution in the simplex technique occurs when it is not possible to determine the basic variable that should leave the basis. Whenever there is this kind of situation, we are not able to determine which variable should move out of the basis, the unbounded solution occurs. This happens when all the constraint coefficients of the non-basic variable that is to enter the basis are negative or 0. So what we do in simplex method, we determine any non-basic variable to enter into the basis based on the criteria, some criterion. Okay, and if in that column all the values are negative or 0, okay, then so that there is no minimum non-negative ratio. So in all these cases, okay, we will get infinite or negative ratios which we don't count. Okay, so there will be no unique minimum non-negative ratio. Okay, and the value of entering variable can be increased indefinitely without violating any of the constraints. That is, the solution space is unbounded. As a result, the objective function value may be increased maximization case or in maximization case, or decreased in case of minimization case indefinitely, because the values of objective function or the value of the objective function depends on the values of the decision variables. Okay, so in this case, both the solution and objective function, solution space and the objective function are unbounded. So the indication for that is if all the values in the entering column are negative or zeros. For example, consider this LPP. Sorry. So, okay, one constraint greater than equal to type 2 or less than equal to type. If we solve this during some intermediate state, okay, during some intermediate simplex table, we find like this. Okay, what we find? This is the entering variable corresponding to most negative value, that is x1, and here you see this is -1, -2, -6. So all the values are negative, or some of them, if some of them are negative and some of them are 0, then this indicates that the solution is unbounded. Okay, here we can see the minimum ratios here -5, -5/2, -5/3. So we don't count negative ratios. Okay, that is, the minimum ratio is not found. We are not able to find the minimum possible ratio. So this is the case of unboundedness. So all the coefficients in the column corresponding to entering variable are negative, therefore this problem has unbounded solution. So whenever you find this kind of situation, you conclude that the solution is unbounded. This LPP has unbounded solution. Okay, so that's all. These are the exceptional cases in LPP.